Now that we've covered a lot of the basics of calculations you can do for a generic, non-complicated transmission line system, let's tie it all together and see how we can use what we've learned to calculate some of the most important quantities for your standard generator transmission line load setup with the phasor standpoint. So when our input signal is a sinusoid. One of the main things that we've also started introducing with some of our calculations. So before we set z equal to 0 on the generator end and z equals L on the load end. For these calculations, since we're using input impedance and all that, we're going to also use the coordinate system where we set the origin to be at the load end. That will make our calculations and our formulas congruent with what we were talking about before. And to summarize, the various things that we want to find include, we want to know what the voltage is that went in, what the current is that went into the transmission line, and we also want to know the voltage at the load and the current at the load, and in the end, brass tacks, how much power actually gets dissipated and successfully delivered to the load. So if you were a utility company, this is the actual amount of power that actually makes it to the consumer that you can charge money for. And then kind of a byproduct is that we also want to know how well matched this system is. So we're going to work our way through and see how we're going to calculate each of these quantities using knowledge that we've had for this transmission system. So the first step is we want to find beta L, since that's a basic quantity that we're going to plug in to find the input impedance. So once you find beta L, you can then go ahead and find the input impedance. So the input impedance, from our previous discussion, is equal to Z naught ZL plus J Z naught tangent of beta L all over, and then you swap the terms in the numerator. So Z naught plus J ZL tangent of beta L. And once you calculate that, it's just going to be some complex number, and you can use this to find out what the voltage is that actually goes into the transmission line. So that is going to give you the impedance over here, and then you can use it in the same manner that you were using Z naught in the case of the time domain calculations. So to find the input impedance going in, or in other words, we can say this is the voltage at U equals minus L. That is going to be equal to the voltage divider between ZG and the input impedance. So VG times Zn over Zn plus Zg. The current, in contrast, in this case, we're just looking at a positive going wave, and so it is just straight up the voltage in divided by the input impedance. So this expression here and this expression here allow us to find the first two of many parameters that we're exploring in this example. Next up, we want to find the reflection coefficient, which we'll use to calculate a bunch of other parameters. So remember that the reflection at the load is going to be equal to ZL new minus old, so ZL minus Z naught over ZL plus Z naught. And that's a key result that is worth highlighting. And note that since we're going to be multiplying and dividing, we're going to be multiplying by gamma L, having this in polar form is pretty useful. So if possible, once you have this, converting it to polar form might be really relevant for the next step, namely to calculate the Viswar. So when you calculate the Viswar, remember S is going to be equal to 1 plus gamma over 1 minus gamma. So if you already have this gamma L in polar form, then the magnitude is ready to just be plugged in here. So calculate that, and then that gives us this here. So now we're halfway there. Now the next step involves slightly more new thoughts or new applications of our existing knowledge. What we want to do now is to find the forward propagating wave V1 plus. Because once we have V1 plus and we have the reflection coefficient, we can then readily find the voltage and the current at the load, and in turn find the power. To find this V1 plus, let's start by pointing out that finding the total voltage at any point in the transmission line is going to be the sum of the positive and negative going wave, where the positive going wave is going to be V1 plus e to the minus j beta u, and the negative going wave will be the reflection, gamma L e to the plus j beta u. If we set u of u is equal to minus L, we can then find the expression of Vin. So that is going to be equal to Vin, which is going to equal to V1 plus, I'm just going to substitute this minus L in here. We get j beta L plus gamma L e to the minus j beta L. And this Vn we also have over here, right? So if we compare these two, we can actually solve for V1 plus. And when we do that, we can then find that V1 plus is going to be equal to Vn all over e to the j beta L plus gamma L e to the minus j beta L, where Vn is what we calculated in step 2. So now we have an expression for V1 plus. We can then use that to find the voltage and the current at the load. So to do that, it's you're probably through the worst of it. The next step isn't that bad, because we'll remember that VL, the voltage at the load, which is also equal to V of u equals to 0, is simply going to be equal to V1 plus times 1 plus gamma. And similarly, the current at the load is going to be equal to VL, which is what you just calculate up there, but you just divide it by ZL. So with that, you have expression for these two terms. And remember, these can be complex quantities because gamma is a complex number, and same with the voltage at the load. It's also going to be a complex number based on what you see here. ZL, 1 plus gamma, V1 plus, all of these can be complex numbers, so these will all have some kind of amplitude and phase expression. Finally, the last thing is to find the time average power. Step 7. Time average power is going to be equal to 1/2 the real part of the voltage at the load, so U equals 0, times the current at the load, U equals 0. But don't forget the conjugate. And once you have these two complex quantities of the voltage at the load and the current at the load, you just plug it into this formula, and then that will give you the time average power that's actually delivered to the load. So as you can see now, using the concepts that we learned before with a little bit of extra manipulation that we haven't seen before in step 5, we can see how we can start out by finding the input impedance. Using that, we can figure out what the voltage and current going in is. If we have the reflection coefficient, we can find the Viswar, which is another quantity of interest. But also with the reflection coefficient, we have this other expression that we have for the positive, for Vin, which we can then equate to what we had in step 2 and come up with an expression for the forward going voltage. And this forward going voltage with gamma will allow us to find the voltage and current at the load, which we can then in turn calculate the final quantity, the time average power, that actually makes it to the load. So with that and our past, you can see that with the past few formulations all tied together, we're able to find a lot of the key parameters of interest in a transmission line system.